In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear, but might not be mathematically rigorous. In particular, we will not use the famous epsilon delta language. In this lecture, we will talk about one of the most important applications of derivatives, that is to find extreme values of a given function. Extreme values means the maximum or minimum value of the function. All right, so first, let's look at the so-called extreme value theorem. This theorem says this: suppose that we have a continuous function, which is fx, so the continuous function of the graph, there's no jump of the graph. So this is a function fx that's defined on a closed interval from a and to b. And then the theorem says you can always find the maximum value, which is right here, right? So in this picture is right here. So this is the maximum value, and it is attained at some point, which here I write as C upper bar. Now, maximum value means at this point you have this FC bar is always no less than any x that's between A and B. And then intuitively clear, you can always find the minimum value. This we call absolute minimum value. Let's say at some point, so here I did not see lower bar, right? Then minimum value means at this point, the value at this point is always no greater than any other point in this interval. Now, for this value we called absolutely minimum, and for this we call absolutely maximum. The theorem says if the function is continuous, you can always find places where the function f has absolute maximum or absolute minimum. Now, of course, it could happen is sometimes those points are not in the interior. So here what happens is in the interior, right? So those are what happens is in the interior. So that's within the open interval, but also could happen, it happens on the endpoints, right? So here, the minimum happens at A, and for example, the maximum could also happen on B, or you can switch it. All right, okay. Now, then the question is, the most important question is how to find, right? We say, okay, so now we know you can, a function is continuous, it always have maximum, minimum on a closed interval, but then most importantly, what we want to see is how to find, right? The place where it is maximum, the place where it's minimal, and those extreme values, right? How to find those extreme values. Now, extreme values means absolute maximum or absolute minimum. All right, for that, we'll use this Fermat's theorem. Fermat's theorem says this: if f has, let's assume f is differentiable, right? Here we assume that f is differentiable. Differentiable at A and B. Okay, if f is differentiable at A and B, then if f has the absolute maximum at some point, then the derivative has to be 0. Now, if have absolute minimum, then the derivative is also 0. Now, intuitively, this is clear. Let's see why is that. Okay, so we say it's proof. This is not completely rigorous, but it's clear enough. All right, so let's look at the picture. I suppose we assume the function is differentiable. So this is x and this is y. And then the function attains a maximum, right? So it attains, okay, so some maximum at some point. This is the C bar, right? Okay, so attains maximum at this. Now, you see, if it attains the maximum, then if you look at the tangent line, it's horizontal. If you look at the tangent line, it has to be horizontal. Now, what does mean horizontal? Means the slope, k equals 0. But how you calculate the slope? The slope we know by the meaning of derivative, by the geometric meaning of the derivative. This is exactly given by the derivative at the point. So we get this one equals 0. Now, similarly, you say, okay, suppose it attains the minimum also in the inside, right, in the interior within A and B. Okay, so this is, let's say, this is A, and this B. Okay, so now here we have a point attains absolute minimum, right? Again, if it's minimum, then you have, if I draw the tangent line at this point, this again has to be horizontal. Everything is above it. And we have the slope. Again, we have the slope is 0. So the slope we know is calculated by the derivative at this point. So we also get that this one is 0. So this is called Fermat's theorem in calculus. If f is differentiable, so assume f is differentiable, and then if f attains absolute maximum at some point or absolute minimum at some point, then the derivative at those places are 0. Okay, for that, we introduce a definition. We say if you have point C that is AB, between AB, so this one is called a critical point. If the derivative at that point equals 0. The Fermat's theorem tells us if f attains absolute maximum or absolute minimum at the point C, then C is a critical number. Here we want to emphasize, okay, so this is important, keep this in mind. We have to emphasize the converse is not true. So that means, okay, recall, the converse is not true. That means if I have a number and I know the derivative at the number is 0, so that's what we call the critical number, right? Then that does not necessarily mean f has maximum or absolute minimum at that point. So here are the two other typical situations of critical numbers. Now look at the first picture. If you look at the first picture, you see we have, this is the absolute maximum, right? You see, okay, so this is the absolute maximum. And here, this one is right here. This is the absolute minimum. However, absolute minimum. However, if you look at the graph, you see some points, right? So this we have here. Here we have, this is the slope is also 0. So here the slope is also 0, right? So the derivative is 0. But those points, they're called the local maximum because locally it is greater than points near it. Locally, it's greater than points near it, but it's not absolute maximum because absolute maximum is the global maximum, which is right here. Now, similarly, if you look at here, these 2 points is also critical points because the slope is 0, it's horizontal, but they are not absolutely minimum. They are called local minimum. So those are called local minimum because locally it's smaller than points near it. All right, so those are called local maximum or local minimum. All right, so those are the places we have. They are also have 0 derivative, but they're not absolute maximum or absolute minimum. Now, another situation is right here. If I look at the fx equals x cubed, right? And then if you look at the derivative, so this is 3x squared, right? Fx is 3x squared. So in particular, if you add 0, you get 0. So here, so for 0, this is a critical point. So this is 0, so this is a critical number. It's a critical number. The slope is 0. However, from the picture, you know, it's clearly, this is neither maximum or minimum. It's not even a local minimum, right? No, not a local extreme value. All right, so here it's two situations where we have the derivative is 0. We have the derivative is 0, but it's not absolute maximum or absolute minimum. Now, based on, if you combine those things together, we have the steps to find absolute maximum, absolute minimum. Suppose I give you a function f equals fx, which is continuous and differentiable f8, and we want to find extreme values. Extreme values means absolute maximum, absolute minimum. So how should we do? Step one, we find the critical numbers. That means the places where the derivative is 0. And then we compute the value of f on those critical numbers. And don't forget, we compute on the 2 endpoints A and B. Don't forget A and B. And step 3, what we to do is we compare all the values from step 2, and we pick the largest one as the maximum, and we pick the smallest one as the absolute minimum. Now, why do we need to evaluate all those numbers. That's because, as we said, okay, so Fermat theorem tells us if it's maximum or minimum, then the derivative is 0. But however, it could happen that we have some other critical numbers. It's not maximum or minimum. And also it could happen that the maximum or minimum, they appear not in the interior, but is on the endpoints. So combine all those things together, the step 3 is necessary. We need to compare all those numbers and pick the largest one as the absolute maximum and the smaller one as absolute minimum. All right, let's implement this. Okay, example 1. Let's find the extreme values of this polynomial. Fx equals x cubed over 3 minus x squared minus 8x plus 10 on the interval, which is 0, 6. Okay, let's do it. Step 1, we find critical numbers. Critical numbers in 0, 8, close interval. Okay, so that for that, we just take the derivative, right? So I take the derivative L prime x. We take the derivative of F prime x. Okay, so we have this is the L prime x. This one equals is x squared minus 2x minus 8 equals 0. And from here, we can factorize this, so x minus 4 and x plus 2 equals 0. Okay, so then we get x equals 4 or x equals negative 2. However, you see, negative, if you look at x negative 2, this is not in the interval 0 and 6. So we ignore this one. We don't need this. All right. And this is the only valid one, x equals 4. Now, step 2, let's evaluate those numbers. So step 2, let's evaluate fx at the critical point, critical number x equals 4 and endpoint x 0 and x equals 6. Okay, let's do it. We have F4. Let's see what is L4. L4 is 3 to the 64 minus 16 minus 32 and plus 10. So which is 364 minus 38. Right, so 38. So this is 21. 21 1/3 minus 38. So okay, so it's 27 negative 27 2/3. Okay, so we get this negative 27 2/3. So this is negative number. Okay, so it's negative 27 2/3. All right, so now let's calculate F6. Right, so we say, okay, now let's calculate F. Okay, now let's calculate the others. Okay, so let's calculate F0. So F0 will just be 10, right? Now, how about F6? F6, if you plug in 2, you get to 72 minus 36 minus 48 and plus 10. And this you get is negative 2, right? Okay, negative 2. So the point is now, you see, we get 3 values. One is this. And then you get this 10, and you get this negative 2. All right. Now, step 3, right? Step 3. Okay, step 3. Step 3. Okay, so we pick the largest. All right, so largest, obviously, it's 10, right? So this is the largest 10. So that's F0 equals 10, which will be the absolute maximum. Therefore, for this case, the absolute maximum attains not in the interior, but on the boundary, which is 0. And then we pick the smallest, right? And smallest, obviously, what you have here is you find, okay, so this is the smallest. That's F4 equals negative 20 over 3. And this is the absolute minimum. So this is the absolute minimum. All right, so we find the absolute maximum is 10, and the absolute minimum is negative 27 and 3/3. All right, now let's look at example 2. Find the extreme values of the function fx equals 2 sine x plus sine 2x on the interval 0 and 2 pi. Again, let's just implement the algorithm. Okay, so step 1, we find the critical numbers. right? Find critical numbers. Then I have L prime x equals 2 sine x, sine x, we know is cosine x, right? Okay, so let's say 2 cosine x plus 2 cosine 2x equals 0. And then we get a trigonometric equation. So that's cosine x plus cosine 2x equals 0. Now we apply, okay, let's recall cosine 2x, cosine 2x equals 2 cosine x squared minus 1. Okay, so then this implies cosine x plus 2 cosine x squared minus 1 equals 0. And if you let this one to be a, so this will be just a plus 2a squared minus 1 equals 0. And you can solve this equation by factorize it. Right, so then you say, okay, I get 2a squared plus a 1 equals 0, and I factorize this, so 2a minus 1 and a plus 1 equals 0, right? Equals 0. Okay, then I get a is 1/2 or a equals -1. Okay, remember that a is cosine x, and then from here we are able to derive the x is equals to pi over 3, or it's 5 pi over 3, or if a is -1, cosine x -1, we know x has to be pi. All right, so we identify 3 critical numbers: pi over 3, pi over 3, and a pi. Okay, so this is step 1. Now step 2, let's evaluate those numbers. So okay, let's evaluate those numbers. Step 2. Evaluate numbers. Okay, so we have this is f pi over 3. We can calculate this. You can see this will just be square root 3 and a plus square root 3 over 2. So it's 2/3 square root 3. And then we have f 5 pi over 3. This one will just do negative. If you calculate this, you just find it's just negative. So it's negative square root of 3, square root 3. And then you calculate f pi, right? So f pi will just be 0. And then you calculate two endpoints of 0, 0, and f2 pi is also 0. Okay, all right. And then you pick the step 3, right? So, okay, now we do a step 3. Step 3, now we pick the largest one and the smallest one, right? And the smallest one. Now, what's the largest one? You find this is the largest one, and this is the smallest one, right? Okay, all right, so then we get this is the absolute maximum, and this one will be the absolute minimum. Absolute minimum, right? Okay. All right, now let's look at example 3. We have fx equals this function. Let's find the extreme values of f on the interval 1 to 3. And then we find the absolute maximum value of f on the whole interval from 1 over 1 to infinity. All right, so let's just apply. Let's take the derivative. Let's take the derivative. So what's f prime x? If you do f prime x, you'll find this is x squared, right? And this is the x times 1 over 2 times x squared minus 1, and then minus x minus 1, right? Minus 1. Okay, so this is the derivative. Right, so step 1. Again, we apply the critical numbers. And then I have fx equals 0, and we can just solve this. You get is x over 2 the square x minus 1 minus the square x equals 0. So from here you get x is twice our x minus 1, and then you get x is 2. Okay, and the 2 is indeed between those 3. So we keep this one, right? We keep this one. Okay. All right, and then let's just evaluate those numbers. Step 2. Let's evaluate numbers. Okay, so we have this F2 equals 1/2, right? F2 is 1/2, and F1 will be 0, and F3 is 3 the square 2. Okay, now we need to pick, okay, so we have 3 values, right? Step 3, we need to pick the largest and the smallest. Now, obviously, this one is the smallest, which is clear. So this one is the smallest. And then we get this is the absolute minimum value. Okay, now let's compare 1/2 and square 2 over 3. Which one is larger? And we find the 1/2 is larger, right? So 1/2, this one is larger than the square 2 over 3. Okay, and then we got this one is the absolute maximum. This absolute maximum. Okay, so then we are done this step. If you want to find the value of, let's look at 2. So if you want to find the value from 1 to infinity, right? So this is 1. If it's 1, we know this is 0. The graph of the function, you see, when x goes to infinity, the fx obviously goes to 0 because the square root, the numerator is square root, and the denominator is x. You see, this is less than the square root of x, and it goes to 0, right? Okay, so the graph will look like this. This is the graph of the function y equals to fx, right? Okay, equals xx, and somewhere it attains the maximum in the whole interval. And because when you find the derivative, you see there's only one critical number. So the critical number has to be here. So this is the 2. It's the only critical number. So this is also the absolute maximum of this function. So it's 1/2. It's 1/2. Okay. All right. So the absolute maximum, this is also 1/2. It's the same as the previous one. Example 4. Find the absolute minimum value of the function on the real line. We know here we are looking for the whole real line, right? If you look at the whole real line and see what happens, obviously when x goes to infinity, the function fx also goes to infinity because this is exponential goes faster than this. F0, we know F0, okay, so F0 equals 1, just right here, right? Okay. All right, so we know it as the function will go like this, eventually go like that. Okay, all right. Now goes to infinity. When x goes to negative infinity, if you look at the x, if x goes to negative infinity, this fx also goes to plus infinity because this one will just go to 0, but this goes to infinity. Okay, anyway, so we know it has to, the absolute minimum has to appear at some point here, And you just all you need to do is just calculate the derivative, right? The derivative equals 0. Let's see how many do we have, right? Okay, so that I calculate, I find, to say, okay, step 1, I find the critical number. If they are multiple, then we have to compare. If I calculate the fx, which equals ex and 2, this equals 0. Oh, okay, so I just get one solution. X is log 2. Okay, so there's only one critical value, so which is log 2, right? And then this tells us this one has to be the minimum. So this has to be the absolute minimum. Okay, so then we just get the value is f, take the 2. Okay, so it's just 2 times log 2. Okay, so this is the absolute minimum. Okay. Okay, so finally, we'll see an interesting application in physics. We are going to use this algorithm to establish the famous Snell's law in a light reflection. Okay, here's the setup. Okay, we have, say, a light start from point A and it goes to point B. and it go from two. It first travel in different medias. So first, say it travels in air, for example, right? Just example, not really, but let's say this is in air, and then it enters water, right? Through an interface, arrives to be. In physics, we know the light, when it goes from one media to another, there's something called light reflection. It's no longer a straight line, right? It's going to change the direction. The question is how it changes the direction, and that's governed by the Snell's law. All right, there's one principle says, light always choose, when light travels, it always choose the path, the quickest path. Quickest path means it takes the least amount of time. All right, so now all we need to do is to just need to find the absolute minimum value of the travel time of the light, right? Okay, let's say this is the point. Assume this is the point that the light chooses to enter the media, let's say water. Okay, we said x, and then the length of this by Pythagorean theorem. By Pythagorean theorem, we know the length of this is the square root of 1 plus x squared, and the length of this will be the square root 1 plus 1 minus x squared. And let's assume the speed of light. For convenience, here we ignore all the unit. Let's say the speed of light in this media, say air, is 2, and speed of light in the water is 1. And then this is how we calculate the travel time, right? It's the distance divided by speed, and the distance divided by speed. So this is travel time. Now, in order to determine where the light chooses to enter the water, we need to find the x. We need to find the x that so that this travel time attains the has the absolute minimum. Okay, so let's apply the algorithm. Okay, so let's apply the algorithm. We just find the critical point, right? We know it's somewhere between 0 and 1, right? It's somewhere between 0 and 1. So we don't check the endpoints. Okay, let's see what do we have. So if I choose step 1, so we say, okay, we just find critical points, critical values. So find critical values, critical numbers, right? If there's more than 1. All right, so then all we need to do is we take a derivative, right? So, okay, let's take the derivative. This is my tx. If I take the derivative, I will get is 1/2/2. This will be x over the square root of 1 plus x squared. And then minus, this will be the square root of 1 plus 1 minus x squared, right? This will be 1 minus x, and I want this one to be 0. Okay, let's see what we have. So from here, I just get 1/2 x over the square root of 1 plus x squared equals 1 minus x and the square root of 1 plus 1 minus x squared. Okay, we get this equality. We get this equality. Let's see what this tells us, right? Okay, if I look at the picture, you see what is the x over x squared plus x 1x. If you look at this, if I look at this angle is theta, let's say this angle is theta 2. And then you find the sine theta 2 will be exactly as x over the square root of 1 plus x squared, right? And I can put this line here. Okay, so this is the same as theta 2. This is a tangent value. If I look at this value, this angle, let's say this angle is theta 1. What is the sine theta? Okay, so for this one, you see, sine theta 1 will be 1 minus x over the square root of 1 plus 1 minus x squared, right? Okay, so that's sine theta 1. So this will be theta 1. So what do we derive? We get, okay, so this guy equals sine theta 2, and this guy equals sine theta 1. All right, and then we derive the equality is sine theta 2 over the speed equals sine theta 1 over the speed, right? Over the speed. And this is exactly the Snell's law. Snell's law tells us when the light travels all right, when it passes through the interface, how the angle changes. So this angle theta2 and theta1 is given by this formulation. And from this derivation, we derive this because we want to find through finding the minimum value of the travel time, and we get this. And of course, you see, how do you know this is the minimum, not the maximum? And that one you can check because it has. So as I said, analytically, if you want to say, okay, why this is the absolute minimum, not the absolute maximum, that's because if you look at the tx equals, if you recall the function 1 plus x squared plus 1 plus 1 minus x squared, right? Okay, you see this function will go to plus infinity if x goes to plus infinity or x goes to negative infinity. So what we have is, we know it has a minimum value, and then the minimum value can be obtained by choosing. So we get from here, we get there is an absolute minimum value. And the absolute minimum value, with the way we find this, we find the critical point, critical number, but because there's only one critical number, so that's why we know that one has to be the absolute minimum. So this analytically, if you want to make things to be rigorous, you know this one, what you find through the Snell's law is the absolute minimum. But anyway, so by just taking the derivatives, find the critical numbers, it's enough to demonstrate how we get the Snell's law by looking at the least amount of traveling time.